Distributed Systems from Scratch. This is episode 19, Formal Verification with TLA Plus, the season 5 opener, the research frontier. By the end of this episode, you'll know how Amazon mathematically proved bugs out of S3 and DynamoDB before writing a line of code. Using a tool built by the same man who invented half the protocols in this series. Seasons 1 through 4 taught you how distributed systems work, the theory, the protocols, the real systems, the advanced topics. Season 5 is different. It's about how we push the field forward, how we prove our protocols are correct, how we build the systems that train today's largest AI models, what the open research problems are, and how to enter the research world yourself. We start with the most rigorous question in all of computer science. How do you prove that a distributed protocol does what you think it does? Here's the problem. A distributed protocol might work correctly for 999,999 executions and fail catastrophically on the millionth. When three specific messages arrive in one specific order during one specific combination of failures. You cannot test every possible interleaving of messages, failures, and timing events. With 5 nodes and 10 messages, the number of possible orderings is astronomical. Each interleaving might trigger a different sequence of states. Some of those states might violate your invariants in ways no test would ever discover. Testing shows the presence of bugs. It cannot show their absence. Testing and formal verification are complementary, not competing. Testing, Jepsen, chaos engineering, fuzz testing runs your actual code under real failure scenarios. It finds common bugs. It tests the implementation, but it can only check the executions it happens to run. Rare edge cases slip through. Formal verification, TLA plus, Alloy, Coq, takes a completely different approach. You write a mathematical specification of your system, a model checker, then explores every reachable state, every possible interleaving of events. If any state violates your correctness properties, it gives you a minimal counterexample. The trade off: verification checks the model, not the code. If the model is a faithful representation of the design, verification gives you confidence that no test can match. But bugs in the implementation, off by one errors, memory corruption, are still the domain of testing. This isn't academic theory. Amazon published a landmark paper in 2015 titled How Amazon Web Services Uses Formal Methods. They reported using TLA Plus on 10 large, complex real world systems, including S3, DynamoDB, and EBS, the core infrastructure behind AWS. In every case, TLA Plus helped them reach a much higher level of confidence in the design. They found bugs that would have been essentially impossible to find through testing, bugs that required specific sequences of multiple failures combined with precise timing conditions. TLA plus, Temporal Logic of Actions, created by Leslie Lamport. Yes, the same Leslie Lamport who invented Paxos, Lamport clocks, Byzantine generals, and latex. He built the protocols and the tool to verify them. Here's what TLA plus does in 4 steps. First, describe the system. Write a mathematical specification that defines what states exist, what transitions are allowed, and what the initial state looks like. You're modeling the design, not the code. Second, define correctness. State the properties your system must satisfy. Safety properties. No two nodes both believe their leader simultaneously. Liveness properties. Every request eventually gets a response. Third, model check. Run the TLC model checker. It systematically explores every reachable state from the initial state. If it finds any state that violates your properties, it produces a counterexample, a minimal sequence of steps that leads to the violation. Fourth, fix and re-verify. Fix the design, update the spec, run TLC again, iterate until no violations are found. Then you have mathematical confidence that your design is correct for the model you specified. Let me show you what a TLA plus specification looks like. This is a simplified spec of two-phase commit from episode 11. We declare variables. RM state tracks each resource manager's state, working, prepared, committed, or aborted. TM state is the transaction manager's state. TM prepared is the set of resource managers that have responded prepared. The init formula defines the starting state. All resource managers are working, the transaction manager is in init, and no one has prepared yet. The consistency invariant is the key safety property. It must never be the case that one resource manager is committed while another is aborted. That would mean the transaction was both committed and rolled back, a catastrophic inconsistency. TLC will explore every possible interleaving of prepare, commit, and abort actions and check that consistency holds in every single reachable state. Here's what the model checker does visually. Starting from the init state, TLC follows every possible transition, every action that could happen, and builds a graph of all reachable states. In this example, it explores outward from init through states S1, S2, S3, branching further at each level. At one state, the one marked bug, it finds that the consistency invariant is violated. TLC reports invariant violated. Trace init to S2 to bug, 3 steps. It gives you the exact sequence of actions that leads to the bug. You don't need to guess or reproduce. TLC gives you the minimal counterexample. In this case, TLC checked nearly 15,000 distinct states in under half a second and found the violation. For small models, it's nearly instantaneous. What did Amazon actually find with TLA plus? On DynamoDB, TLA plus found a subtle bug in a new replication protocol that would have caused data loss. The bug required a specific sequence of 3 failures combined with a network partition, a scenario virtually impossible to reproduce in testing. On S3, they verified a new background repair process and discovered that a planned optimization would have introduced a rare data corruption scenario. They caught it before it was implemented. On ABS, TLA Plus found a race condition in volume failover logic that had evaded months of testing. In every case, the bugs were in the design, not the code. Even perfect code would have exhibited these bugs because the algorithm itself was flawed. Code level testing, unit tests, integration tests, even Jepsen would never have found them. TLA Plus verifies two kinds of properties. Safety properties say nothing bad happens. No two leaders simultaneously. No committed value was never proposed. No resource manager committed while another aborted. Safety is checked as an invariant at every reachable state. If it's violated anywhere, TLC reports it. Liveness properties say something good eventually happens. Every valid request eventually gets a response. A leader is eventually elected. A committed write eventually becomes visible to readers. Liveness is checked as a temporal property over infinite execution traces. This connects back to episode 6. We said Paxos guarantees safety always, but liveness only when a leader is eventually stable. TLA plus lets you formalize exactly that distinction and verify each independently. Here's the main limitation of model checking state explosion. For a simple two-phase commit with two resource managers, TLC explores about 50 states. Instant. For Raft with 3 nodes, the state space grows to around 500,000 states. Still manageable, a few seconds. For Raft with 5 nodes, the state space explodes to billions. Hours of computation or simply infeasible. The state space grows exponentially with the number of nodes, messages in flight, and failure modes. This is fundamental. It's not a limitation of TLC specifically, but of model checking in general. How do practitioners deal with the state space explosion? First, verify small models. Use 2 to 3 nodes, not 5 or 7. Bugs that exist with 3 nodes almost always exist with 100 nodes too. The protocol logic is the same. Second, symmetry reduction. If all nodes run the same code, don't explore permutations separately. Node 1 being leader is symmetrically equivalent to node 2 being leader. Third, abstraction. Model the essential logic, not every implementation detail. Represent the network as a set of messages, not as TCP connections with sequence numbers. Abstract away irrelevant details. Fourth, bounded model checking. Check up to a fixed depth, say 20 steps. This won't prove the absence of all bugs, but it finds most practical bugs within reasonable time. Leslie Lamport created TLA Plus in the 1990s, but that was decades after he had already invented the protocols that the tool is designed to verify. Lamport Clocks, 1978. Episode 3, Paxos, 1989. Episode 6, Byzantine Generals, 1982. Episode 18, and TLA Plus, the tool to verify them all. Lamport's philosophical position is clear. If you can't formally specify your algorithm, you don't understand it well enough to implement it. The specification is the understanding. The model checker is just the validation. Lamport wrote the definitive TLA plus specification of Paxos. The Raft authors wrote a TLA plus spec to verify their protocol. CockroachDB uses TLA plus for its transaction model. The tool is used in production by engineers at scale. Here's the practical workflow. Step 1. Write the specification in TLA plus or Pluscal. Pluscal is an imperative style language. It looks more like pseudocode that compiles to TLA plus. It's easier to learn for engineers coming from programming backgrounds. Step 2. Define your properties, the safety invariants and liveness conditions. Step 3. Run TLC. If it finds a violation, it gives you a counterexample trace, the exact sequence of steps that leads to the bug. Step 4. Fix the specification, which means fixing the design. Rerun TLC. Repeat until no violations are found. The tools. TLA plus Toolbox is the IDE. TLC is the model checker. TLAPS is a proof system for formal mathematical proofs, though most practitioners use TLC. The learning curve is real. TLA plus is a mathematical notation, not a programming language, but Pluscal reduces the barrier significantly. Most engineers can write a useful spec within a week of learning. TLA Plus isn't the only verification tool. Let me give you the landscape. Alloy uses relational model checking, good for data, model constraints, and API specifications. More lightweight than TLA Plus. Kokyu and Isabel are interactive theorem provers. Instead of model checking, which explores states, they construct mathematical proofs. The SIL4 microkernel was formally verified in Isabel. CompCert, a verified C compiler, was verified in Coq. These tools provide the strongest guarantees but require significant expertise. P. Developed at Microsoft models asynchronous state machines, used to verify Azure protocols and USB drivers. Spin with the Promela language is another model checker used extensively at NASA for verifying spacecraft protocols. For distributed systems specifically, TLA Plus is the dominant tool. It was designed for this exact domain. When should you invest in formal verification? Use it for new consensus or replication protocols, distributed transaction logic, failure recovery mechanisms, leader election protocols, anything where a bug means data loss or inconsistency, anything with complex interleavings that testing can't cover. Don't use it for CRUD application logic. Well understood protocols. If you're just using Raft, use a proven implementation, performance optimization, UI, or business logic. When a battle tested library already exists, the cost is days to write the spec. The return is a level of confidence that no amount of testing can provide. Chris Newcomb, the Amazon engineer who led the TLA plus adoption at AWS, said something profound. The main benefit of writing a TLA plus spec isn't running the model checker. It's the clarity of thought that comes from forcing yourself to precisely describe the system. Writing a spec forces you to answer the fundamental design questions. What are all the possible states? What transitions are allowed? What must always be true? What must eventually happen? These are exactly the right questions to ask about any distributed system. The spec is valuable even if you never run the model checker. Connections to the series. Paxos from episode 6. Lamport's TLA plus specification of Paxos is the definitive, unambiguous reference for the protocol. Raft from episode 7. Ongaro's dissertation includes a TLA plus specification that was used to verify safety properties. The 2PC blocking problem from episode 11. The in doubt state is exactly the kind of design level bug TLA plus is built to find. A reachable state that violates a liveness property. Jepsen from episode 10. Jepsen tests the implementation. TLA plus verifies the design. They are complementary, not competing. Use both. Let's recap. 1. Testing checks some executions. TLA plus checks all reachable states. It finds design bugs that are impossible to find through testing. 2. Amazon uses TLA plus on S3, Dynamo, DB, and EBS. They found critical design bugs that had evaded months of testing. 3. Safety properties say nothing bad happens. Liveness properties say something good eventually happens. Both are verifiable. 4. State space explosion limits model size. Verify small models. Abstract aggressively. Use bounded checking. 5. The biggest value of TLA plus is the thinking, not the tool. The discipline of writing a precise specification reveals design flaws before a single line of code is written. Next episode, distributed ML systems. How do you train a model with 175 billion parameters across 10,000 GPUs? Parameter servers all reduce. Data parallelism, model parallelism, and pipeline parallelism. The distributed systems concepts we've learned: partitioning, replication, fault tolerance applied to the hottest workload in computing. That's episode 19. Formal verification with TLA plus, proving that your distributed protocols do what you think they do. Next time, distributed ML systems. Thanks for watching.